Sir, today I Mohammad Samir and Guraji Singh Bhattu is here to present our communication system project in which our topic is wireless infrared communication between two computers. And this is our aim of this project to send data using infrared waves by using IR LED to send waves and receiver called as TSOP1838 along with Arduino Nano. Infrared technology is used wireless technology as wireless communication implies the exchange of data as electromagnetic energy between two devices without use of wire or cable. Now let us have a quick discussion about infrared waves. Infrared wave is a part of electromagnetic spectrum with wavelength more than visible light, and hence it is undetected by naked eyes. Basically, it has a wavelength of about 700 nanometer to about 1 millimeter, and it was discovered by Sir William Herschel, and it has a frequency of about 430 terahertz to 300 gigahertz. It can pass through glass but not through opaque barriers, so they are limited to room in which they are generated. This limitation secures transmission and prevent from interference. Infrared communication is basically of two types. First one, point to point. It requires a single line of sight between transmitter and receiver, and the second one is diffuse point. In this, there is no line of sight, but link is maintained by reflecting transmitted signals. Now, the advantages of this IR communication is security, safety, high-speed data communication, etc. Basically, the data rate of infrared communication are as follows. First, serial infrared has a data rate of 300 to 1,15,200 bit per second, and fast infrared of about 4 megabyte per second. Infrared rays is divided into basically three parts: far infrared of 1 mm to 10 micrometer, and mid infrared 10 to 2.5 micrometer, and near infrared 2500 to 750 nanometer. Basically, in this modulating in IR, we use pulse position modulation. It is a modulating scheme in which the amplitude and the width of pulses are kept constant while the position of each pulse with reference to the position of reference pulse varies according to modulating signal. It is done in according to the pulse width modulation signal like this. Each trailing of pulse width modulated signal becomes starting point for the pulse in ppm. Position of pulse is proportional to the width of PWM pulse or pulse width modulation pulse. Basically, to send data between two computers, we use two protocols. First is NEC protocol, which is this. The NEC protocol is widely used in a remote control. In this, it encodes remote keys to a 32-bit frame format in which start pulse is there and then a address of 8-bit from 0 to 7 and then a complement of address, then there is command and inverse of command and end of message and a total of 32 bits. It uses pulse distance encoding scheme. In this, each bit is composed of carrier modulated pulse and space. Space width distinguish between logic 1 and logic 0, and carrier time between consecutive bursts differs depending on whether a logical 0 or a logic 1 is being transmitted. Here the carrier frequency is basically about 38 kilohertz for basically logical 0. We have a 562.5 microsecond pulse burst followed by a 562.5 microsecond space with total transmitted time of 1.12 millisecond. Logical 1 Logical 1 has a 562.5 microsecond pulse burst followed by 1.6875 space with total transmitted time of 2.25. Whenever a key is pressed of a remote control, the message transmit consists of 9 millisecond leading pulse burst, a 4.5 millisecond space, 8-bit address, its inverse command and its inverse, and a final a 562.5 microsecond pulse burst to signify end of message transmission. And if the remote control get pressed, then a repeated code will be issued, which is like this. Which is like this. Then a repeat code will be issued of 40 millisecond after a pulse burst that signifies that end of message, and repeat code will continue and send out at 108 milliseconds until key is released. So it finally consists of 9 millisecond, 2.55 millisecond space, and a 562.5 microsecond pulse burst to mark the end of the space. And the next one is UART protocol. It basically stands for Universal Asynchronous Receiver and Transmitter, as there is no clock to synchronize. Here we use serial data transfer. Here serial is basically through wires. Here data is transferred bit by bit using a single wire. UART is a form of device to device hardware communication protocol, and it basically uses two wire for transmitting and receiving. Two UART directly communicate with each other, with one received to other transmitter and second one is vice versa. Transmitting UART is connected to controlling data bus that sends data, which is this data bus. Transmitting UART is connected to controlling data bus that sends data in parallel form, and data is transmitted bit by bit, and at the end it is converted back. Here it is converted back to parallel. Here a band rate should be same, a baud rate should be set same on both transmitting and receiving line. In this mode of transmission is a form of, in which a packet it consists of a start bit, data frame, parity bus, and a stop bits. As there is no clock, so it work at normally as bus it at a high voltage, and to tell receiver that the data is going to start, to indicate that we should have a start bit, which we use is at active low, and after that data is there, and after that we have data, and at the end it has and stop bit there and a parity checker bit also. Here you can see it's in parallel, and after that it is connected to UART, which convert parallel to serial, and this serial is transported from receiver of one to transmitter of second, likewise and versa, and then after that it is the then after that it is connected to parallel again. For example, if at a start there is, let 0 is the one which show it is going to start, let there be a number 1 0 0 1 0 1 0 1. At by checking its parity, we found that its parity is 0 and stop bit 1. After it reaches the end, here this start bit, parity bit and stop bit all are removed, and only the data rate is passed. So, and after that we have some components and which we use in our project. This is TSOP 1738 and an IR LED. An IR LED or IR sensor is used to give out IR rays. It emits basically a frequency of 38 kilohertz, and In remote, it uses NEC protocol, and a TSOP is a IR receiver. IR receiver. It consists of a pin diode to convert optical signal to electrical and pass these through AGC automatic gain control to eliminate unwanted disturbance and from signal, and pass through a band pass filter, and lastly through demodulator to remove carrier frequency and get the original signals. And after that we have Arduino UNO, which will be explained by Mr. Gurajis.
Good morning, sir. The aim of this project is to send data between two computers uh, using infrared waves. So we have done that in a total of two ways. Firstly, using the NEC protocol, which is commonly used in TV remotes and other electronics. Let me focus this. So over here, uh, on this computer, we are generating 32 random bits, and according to those bits we are deciding how long each pulse and each space will be for according to the NEC protocol, and we are sending it to the uh, uh, other computer. On the other computer, we of course we have hooked up this Arduino Nano with a TSOP. The NEC protocol uses a 38 kilohertz carrier frequency, and the TSOP 1838 over here is designed to be able to demodulate that. And on this computer, uh, this code will read what has been sent and will display that. So we wait for it to upload. The other one is done. So over here we can see it is receiving bits from the other PC, and on the other PC we can see the bits that it is generating, and we can visually confirm that these are these all of these are the same, and data is being transmitted between these two computers. And now I will explain the code which is being used to send data between the two computers. Firstly, we are including this library irremote.h. This will help us, and declaring an object of this class irsend. Okay, so we will be sending random bits. We will be generating those bits randomly. So srand 0, we are initializing the randomizer, and so this is the 38 kilohertz frequency. We have just put this value in this integer, and we have two arrays. This is integer array and an array of the bits that we want to send. This array will contain all the timings that will be used to send this. So basically in this will be showed for how long the pulse is being transmitted, and also the gaps between the pulses. Okay, so this will put random bits in this array. So of course the first two elements in the IR signal array, of course for NEC protocol we have to for before sending a message we have a 9 millisecond pulse, and then a 4.5 millisecond 4.5 millisecond gap, and after that, depending on what the value of the bits that we want to send, we will be putting the values accordingly in this IR send array. This code reads the value in the bits array and assigns for how long the pulses and the gaps between the pulses will be. and of course after all of that the ending uh, 560 uh, microsecond pulse. And this function, it is an inbuilt function of this library. We are telling it we have to send this array. There are total this many uh, this many elements in this array, and this frequency which we have defined here as 38 kilohertz, which is required for NEC. And after that we have just printed the uh, bits that we have sent using this. This just prints the bits in this array. And for the receiving part, this one, uh, okay, so of course we are using the same library, and of course the uh, object of this class. If a signal is received, of course this void loop keeps on looping. If a signal is received, it will put this in this variable, this results variable, and it is calling this function, which of course prints bits received and the value inside it. We don't need us to write a very detailed program to decode NEC, because it is already available to us. We don't have to check what are the timings, because NEC is a very widely used protocol, and it is easier to uh, just write this code. It will decode it for us and just show us the value in binary. This specifies binary here. Usually hex is used, but we are sending bits between these two computers. The Arduino Nano and Uno and other boards also have the capability of using UART for serial communication. And over here we have used that. We have connected the transmission and receiving the pins of these Arduino to infrared LEDs and circuit using a photodiode, and we will use these along with Python using the library PySerial to send data between these two computers. Uh, open Notepad. Okay, so this code over here will read values from this uh, CSV file, and we'll send it over to that computer, where we will see another where the Python code will make a new file with that data in it. So let's get this, and yes, so we can see data is being received on that computer. And a new text file has been made. The transfer is still going on. And so it has been completed. And this file has all the data from this file that we sent. And we do have to make sure the baud rate is same between this computer, and also the sketch we are uploading into the the very simple sketch that we are uploading into our Arduino, which is just to be able to receive and send. This this just does nothing. It just this is the one for the computer that is receiving the data. It will just uh, of course the connection you can see we have made using the photodiode is done to the is connected to the receiver pin. So of course this will just p- have this will so another thing, we have to make sure the baud rate is same between this code and this code. So of course they have to be communicating on the same baud rate. And also in the simple of the Arduino sketches for this one is of course very simple. Though this for the transmitter, we have directly taken it from the receiver RX pin, so we don't even need to write anything here. And for the receiver one, of course, the it will read the data it has received and just print it again. The Pi serial will be able to receive it.